Hello.
Yes,
do you
we
hear
can
me?
hear you, Danila. So
Nice to, yeah, thank you so much. I wanted to thank all organizers, first of all, for the opportunity to present at this wonderful event. I think it's very unique. And today I want to talk a little bit more about theoretical subjects. Not really theoretical, more like phenomenological, using chemical kinetics to describe spin dynamics, not spin dynamics, dynamics in hyperpolarized systems such as PHIP and SABRE. And I even going to probably derive some equations, so forgive me if you already know all of this, what I'm going to show about. The lecture is going to be more like educational. At the same time, if you want to engage, please feel free to use pen or pencil and piece of paper and follow me with my derivations. So, and I wanted to start with saying that I would not be here literally today speaking with you about science if not my friend and advisor, Kirill Kovtunov, who unfortunately passed away recently due to complications in health. But in a sense, it brought me to thinking, even events like that bring you to think about the nature of reality, nature of information, what is information. And I think even in my talk today, I will touch a little bit on these subjects, more like very fundamental, very deep, maybe going into physics and even related to cosmology and black holes. But Kirill was the one who actually met with Eduard Chekmenev, who also organized this conference. And basically, because of their meeting and their interaction, I eventually came to Vanderbilt and later came to Berkeley. So I'm totally quantum mechanically entangled with people like Kirill and Ed. And once again, I want to thank my advisors for opportunity to be here today. So and during our visit at Vanderbilt in 2013, we were fortunate to actually discover high-field SABRE effect. And we never planned on doing SABRE when we were coming to Vanderbilt. And actually, personally, Kirill and I, at that point in time, did not believe that SABRE is actually physico-chemical effect. We thought it's just purely exchange. And that was actually our first attempt goal to maybe see if SABRE is just chemical exchange process and there's no this spin dynamics, because we couldn't understand it at that time. But luckily, by doing experiments, we not only realized that, no, it's actually spin dynamics, spin dynamical process, but we also were fortunate to discover this new high-field SABRE effect. And this is just a few images of us working at about 12 at night with Ed Chekmenev, Roma Shepin, Aaron, Milton, and Kirill. And with that, I wanted to start with asking a question. So, what is the goal of science? What is the purpose of science? I think many of us believe that part of it is application. We're going to bring very interesting new applications to the world, which will help us to improve as a society, to improve our well-being. But at the same time, to me, I think science sometimes is about puzzles, about answering interesting questions. And the analogy of a puzzle, I think, very interesting, because once you start putting the picture from individual constituents, you come up with a bigger kind of idea, bigger picture from which you now can look at the problems with a much deeper view. And with that, that's the way how I look at the processes in parahydrogen, involved in parahydrogen, such as parahydrogen-induced polarization and signal amplification by reversible exchange. And in general, the concept of magnetization transfer catalysis, which was coined by Professor Duckett, as well as the method of SABRE coined by Professor Duckett. So I think it's a very, very powerful concept. So what do we have here? We have a source of spin order, parahydrogen, either coming to a reaction product, and in that case, we have parahydrogen-induced polarization. If it's just one-way reaction, A goes to B. Or we can have more complicated exchange process, and in that case, parahydrogen can dissociate, substrate can dissociate, and we have a process of SABRE. And I think by introducing so-called hyperpolarized species, which I will do in a couple of slides, we can unite and look at this process in a more holistic way, in general, which can eventually help us to think about experiments and help us to maximize reaction parameters and optimize reaction parameters to optimize signals. So yes, SABRE was introduced in 2009 by the group of Professor Duckett, and the main prerequisite of SABRE is reversible exchange of hydrogen, which can reversibly exchange with a free-forming solution and acquire new singlet order each time. And you have your substrate, which can also reversibly exchange with the complex. And by doing so, if timing of the lifetime of the complex is good enough and satisfies certain parameters, which we will talk about today, you can have coherent polarization transfer from parahydrogen to the substrate, and polarization will accumulate in a free substrate in solution. SABRE was very well explained. The main spin dynamical factors of SABRE were very well explained in a paper by Andrei Pravdivtsev and Konstantin Ivanov, where they talk about the concept of level anti-crossings. So indeed, the simplest spin system which is suitable, and I'm apologizing that I'm starting from SABRE, but I think SABRE is a little bit more interesting case, and we're gonna look at it. But parahydrogen, we also touch it, parahydrogen-induced polarization. But I think it's more interesting to talk about SABRE as this newly evolving phenomenon. So the simplest spin system which is suitable for describing SABRE is three-spin system where you have two spins, A prime, coming from parahydrogen, and the third spin, we assume that our substrate has only one spin. And in that case, you can show that you're gonna have, if you plot energy level diagrams in which the first state written in singlet triplet basis describes the state of two spins in hydride, and the third spin, alpha or beta, describes the state of the third spin in the substrate, you can clearly show that you're gonna have one level anti-crossing between states singlet alpha and triplet plus beta. So what does it mean? Imagine, very simply speaking, that initially you don't have polarization in your substrate. You have all equal amount of alpha and beta spins. And now you start pumping singlet state in the form of hydrides in the system. So this are the spin states that you're gonna overpopulate, singlet alpha and singlet beta. But only singlet alpha have level anti-crossing. So singlet alpha will transition into triplet plus beta, while singlet beta will stay singlet alpha, singlet beta. You don't have any level anti-crossings here. So you can see that from nothing, from zero polarization on your substrate, you now acquired complete polarization of your substrate. So it's a very simple way, very almost like without any math, to explain the essence of SABRE. But I think it's very important also to talk in terms of chemical kinetics. Okay, we know now the magnetic fields, and Andrei and Konstantin and other people in the field now can very well predict magnetic field dependence of SABRE effects. And I think it's still very important to understand what are the concentration and relaxation dependence of these effects. And here I want to start with introducing the concept of hyperpolarized singlet triplet imbalance, basically. So I write it that way. We have hydrogen, and square brackets represent concentration. And we define it as concentration of hydrogen molecules in solution, which are in a singlet state. And as it's imbalance, we're going to subtract concentration of hydrogen molecules in solution, which are in a triplet state, but we're going to normalize by the number of states, which is 3 triplet states. And realizing that orthohydrogen is actually 1 minus parahydrogen, molar fraction of parahydrogen, we're going to have very famous coefficient, which actually shows up in all PHIP and SABRE experiments. 4x, or fraction of parahydrogen, minus 1 divided by 3. So let's see what it means. It means if fraction of parahydrogen equals to 1, we're going to have all concentration of basically of hydrogen is in this hyperpolarized, fictitious hyperpolarized species H2 star. If our fraction of parahydrogen normal means 1/4, like in normal hydrogen, you're going to have 0, right? So that means, let me change the color. That means that in principle, these are the limits in which we operate. We have this fictitious hyperpolarized chemical species that can basically decay to 0 because we're basically talking about magnetization, difference between spin states, corresponding spin states. But I think this approach is very useful if you want to talk about further reactions. For example, you want to say that now this spin order, which is stored here, can transfer to some other states, which can also decay to 0, or maybe it can go somewhere. And the main important point here is that transition will be proportional to the reaction rate times some coefficient, which will include these magnetic field effects. It will include the symmetry constraints on spin dynamics, for example. But luckily, in case of parahydrogen from singlet state, you can transfer 100% of spin order into magnetization. But in more complicated situations, you need to take into account this fact that even though chemically these reactions are possible, you can have magnetic and spin dynamics constraints here. So let me see if I can. So and now, in order to describe SABRE, we need to also take into account kinetics. Let's start with, again, writing that the source of spin order is hydrogen, which can then go into hyperpolarized complex, which we call with the letter C. And then the polarization can be transferred into hyperpolarized substrate. And we also have relaxation effects. And we, for simplicity, first assume that we fully saturate our solution with parahydrogen. So this is basically a scheme to describe the so-called phenomenologically SABRE process. And what we only need to know, now we need to put the corresponding reaction rates here. And obviously here, we're going to call it relaxation of the complex. Here we're going to call relaxation rate of the substrate. This is, as you can see, if you really look at the dynamics of exchange of substrate in the typical SABRE complex, this rate is proportional to the dissociation constant for the substrate. My light is turning off all the time in this building. And you have the coefficient, which we call polarization transfer coefficient, which again, we put all the magnetic field dependence, all spin dynamics in the complex in this coefficient. And here you're going to have some rate of supply, which we will, if you follow really actual spin dynamics in the SABRE system, you will learn that exchange of the substrate and hydrogen is proportional to the concentration of hydrogen in solution and proportional to the concentration of complex in solution and inversely proportional to the concentration of substrate, because you need to form this complex, you need to dissociate one substrate first in order for hydrogen to exchange. So it was beautifully shown in experiments done again in the group of Professor Duckett using XC, where they studied kinetic rates of exchange and dependence on concentrations of hydrogen and substrate in solution. And this is actually what you can show. So what we can do with that, now you write down basically this kinetic scheme. And what you need to find now, if you want to ask what is enhancement factor for the substrate of interest, enhancement factor is going to be proportional to our polarization. Basically, the way we define it is this: S divided by concentration of actual concentration of S. And you solve these equations for stationary conditions. This is why this is actually very simple equations. You can solve them just analytically, and you can derive the equation for the maximum possible enhancement factor in SABRE experiments. And it's a relatively simple equation, again, but at the same time, it shows which and what parameters we need to optimize in order to achieve maximum signal. And it turns out, surprisingly, that dissociation rate constants are relatively easy to control, first by temperature, and second by the nature of the ligand and nature of some ligand parameters such as ortho groups in the iMesh catalyst. But surprisingly, very important to realize that it's simply proportional to the, basically T1, inversely proportional to the relaxation rate in the complex. So if you want to maximize SABRE, if you want to maximize polarization, you need to minimize losses, which is a very obvious kind of conclusion, yet now we at least have some methodological equations to play with to confirm that. And remarkably, this simple equation was able at that time, in 2016, explain some dependencies of polarization on different chemical parameters, such as concentrations of substrates in different experiments, including heteronuclear SABRE experiments and experiments with protons. So in those moments, when you realize that it's actually that easy to solve equations just on the paper, yet they still can be very useful, that's, for me, was one of those days, like a puzzle, and clicked something. And I think just for every young researcher who is watching, I think there is still a lot to be understood in SABRE, PHIP, in general hyperpolarization. So don't be afraid to do something simple. Maybe it can be actually useful. And people like, again, Professor Duckett were able to study a lot of different complexes and indeed demonstrate that this formula holds true in many situations. And a remarkable, very simple conclusion that you can make, that if you deuterate your ligand, if you deuterate your substrate, you will obviously increase relaxation times in the complex because you minimize dipolar relaxation sink, which is usually present if you have protons here. But if you put deuterium atoms, which have lower germagnetic ratio, you minimize relaxation losses in the complex, and you can maximize your polarization dramatically in SABRE experiments. So in case of parahydrogen-induced polarization, situation is kind of simpler. You have just one reaction. Reagent reacts with hydrogen, and you have hyperpolarized product, which then now can decay with the relaxation rate. And I want to point out that maybe we not always do these things right. And I think I will spend a little bit of time, maybe 3 minutes here to explain it. I think we need to take into account that the concentration of product changes as a function of time. So in simply speaking, in very simple terms, you can derive this equation of accumulation of your product as a function of time, in which K actually should be a function of some concentrations in the system and maybe some other parameters of the system. So it may be not always possible to just describe the reaction of hydrogenation with this simple monomolecular reaction. And this equation was derived in many papers, and I want to even point out that very recent paper by Dagis and Malcolm Levitt, they also use kinetic analysis, and it's a very somewhat similar equations you can derive. But I think it's important to point out that we derive dependence of polarization as a function of time, but we also have concentration of the product changes in the function of time. So if you really want to talk about enhancement factor, in fact, it's going to be dependent on time, because I think this is something we usually ignore and just report enhancement factor as a single parameter, but in fact, it will change as a function of time, and maybe actually the efficiency of parahydrogen addition may change also as reaction progress. So I think we should all pay more attention to that. And I don't think I have too much time to describe that, but I was lately during the COVID time refreshing my undergraduate course in thermodynamics of non-equilibrium processes by Valentin Parmon, who was a director of Institute of Catalysis in Novosibirsk. And I found out that there is indeed very useful way of writing down equations, chemical kinetic equations, using thermodynamic basically form. So imagine if you have some part of the reaction, A goes to B, And you don't only have a one-way reaction from left to right, but you actually have from left to right and from right to left. So it's writing down chemical kinetic equations can become messy. But if you express reaction, you can show that you can use thermodynamics to express reaction in such a way where I will explain in a second what does this means. So this parameter contains all kinetic and basically thermodynamic information of the transition state of the system, and it can be written that way. And this is so-called thermodynamic rush. It's a very interesting concept, but it's true that it's possible, it's completely possible to write down all reactions, kinetic reactions using this approach. And why is it useful? Because it becomes very similar to Ohm's law. If you look at Ohm's law, it's usually something like that. You have current, which is proportional to the difference between, sorry for my writing is not very clear, but current between 2 points A and B will be proportional to the difference between basically voltages divided by resistance. And if this is inverse resistance, basically you can simulate all reactions, simulate them, especially in stationary conditions. You can simulate them as just basically Ohm's law as an electric scheme. And that way of writing equations actually helps to think in terms of chemistry in general. So imagine you have these barriers, but you can still push by putting more concentration of your reagent on one side. And by doing that, you will increase reaction thermodynamic rush in the system, and eventually your reaction will go forward. So, and I think this concept, I don't have, unfortunately, enough time, but I checked it with multiple systems. Indeed, in SABRE, you can write down equations in the following way. And I checked it works. It's amazing. It's very simple. So where you just replace it by resistances, let's say it's R1, R2, R3, R4. And what you're looking for, if you're looking for, let's say, concentration of hyperpolarized product here, you need to find a current that is flowing through this part of the system where you have total current this way. And you indeed can show that you will derive the same equation. Again, in this simple scheme, I did not take into account that it can come back. But once again, using thermodynamic form of writing kinetic equations, you can actually do that. And you can derive the same equation. And yeah, just recently also, another paper by Edward was published, which shows, and they did a beautiful experiment where the relaxation in the complex is very short. It will dominate and it will go basic as inverse T1. So your enhancement factor will be proportional to T1 in the complex in case it's very short. And they did a very beautiful experiment where they used exactly the same concentration for reaction parameters in the system. And they just changed the number of quadrupolar nuclei in the system. And they showed that indeed, basically polarization or enhancement factor scales linearly with T1 in the complex. So I think it also confirms the eligibility of these arguments. And I am working on right now trying to use this for describing SABRE relay process. It's becoming a little messy and complicated, but hopefully using some simplifications, we might be able to come with some interesting and important conclusions, including SABRE relay. And in general, I started this presentation talking about maybe trying to look at the problem holistically. I think in general, I'm more and more looking at these things as maybe almost like a new field, nuclear spin chemistry, where you have a conventional chemistry and it can be completely in stationary conditions, nothing is happening, but you have a flow of spin order propagating from one species to another. And I know that we already have a field of spin chemistry, which talks about effects of electron spins and chemically induced dynamic nuclear polarization in chemistry. But I think we can call this I would try to introduce this as nuclear spin chemistry, because indeed, I think we just tip in the top of the iceberg, and you can think of these processes in many different ways as different chemical reactions that happening, or you can think of it as different physical transformations that can happen on the substrate once you produce hyperpolarized product, or a product in which nuclear spin states, certain nuclear spin states are populated. And then you can do some physical transformation with the sample. And we recently collaborated with James Ailes, who pioneered this beautiful reaction production of a very important hyperpolarized substrate fumarate. And I think this substrate has a lot of potential in clinics, not only in clinics, for all sorts of new interesting applications. And I think what he's going to talk soon, I'm not going to step on what he's going to talk about, but I think it's a remarkable new achievement. And it's definitely an example of nuclear spin chemistry of what I'm talking about, where we can manipulate spin order and capture it whenever we want, capture it in space and time. And I'm very happy to be part of this field. And I wanted to finish, again, maybe a little bit metaphysically. So if you look at this system where you have chemistry happening, so seemingly nothing is going on, unless you really know what to look at. You know that you need to look at nuclear spin states. You know that you need to look at magnetization at certain fields. You know how to detect it, and only in that case you are able to extract information from the system and study it. Otherwise, it looks like a normal chemical reaction and nothing's going on. So it brings me to realization that indeed information in the universe, and this is a Leonard Susskind concept of holographic universe, that information in the universe is conserved, it transfers from one form to another, and basically if you're not able to understand what this information means, it's your problem. You're just not able to decode it. You maybe don't have enough knowledge how to decode it. So I think it's a very deep concept, and it brings me back to this field of nuclear spin chemistry, which we are all witnessing right now. And I think we are just really staying right here. And very soon we're gonna have a lot of new discoveries in this field. So thank you so much for that. And thank you, Kirill, once again. And thank you all for your attention.
Yeah, thank you so much, Danila, for this amazing talk. There are many questions about your nuclear spin chemistry, and I would like to get right into it. First question is your thermodynamic rush similar or the same as the chemical potential?
Yeah, it's very, very similar. It's a slightly different thing. So it's actually, chemical potential is this. Chemical potential, you write down like, for the component, let's say alpha, as mu0 plus RT logarithm of concentration. And also sometimes it's actually activity here. So if you have coefficient, activity coefficient. So, but rush, thermodynamic rush is simply exponential of this divided by RT, alpha. So it's basically the same thing in terms of chemical potential. So you can draw kind of chemical potentials. They're also gonna follow this letter or thermodynamic rushes. But strictly speaking, this is how you write it if you follow the derivations in this book. I really recommend everyone to go through. It's a little bit more applications in catalysis, but my background is catalysis. This is how I was aware of this book. But I think it's very useful for maybe describing these complicated processes. I hope that it's more useful than useless. We'll see.
Oh, yeah, thank you very much. So what would play the role of a capacitance in your network?
Oh, interesting question. I don't think there's a capacitance here, but maybe by introducing capacitance, you actually may be able to simulate some coherent dynamics, but I don't think so. So because it's incoherent, maybe I haven't mentioned here, right? Everything that I'm talking here are incoherent dynamics. So we're not taking into account coherent processes, which actually happen during even SABRE build-up. So you can form coherences, right, if you work in a certain field, but we assume that everything is averaged out and you only building up certain populations, which eventually is translated to build-up of these chemical species, which again can be governed by kinetic rate. So it's all incoherent. Therefore, we don't have any oscillations in the system yet.
Okay, so this means that it will get way more crazy if you include things like flow one day, because all these people are showing flow reactors now, right? And
all people what?
Are showing flow reactors or continuous flow presentations, just like Marcel Lutz did in the prior.
Mm-hmm. No, I think, yeah, I think this approach may find applications, especially in parahydrogen experiments where you have stationary conditions, no matter whether it's SABRE or PHIP under constant flow, let's say, of reagents. You're going to have some gradient, maybe. Let's say you work on your microchip. But I think this approach works especially well in stationary conditions. Yeah, because it allows you to simply solve equations. And once again, there is nothing fundamentally unique about this kind of way of looking at things. When you talk about that, let's say, complex C, the change of complex C in time equals to 0, it's equivalent to say that change in charge, there is no accumulation of charge at the point right on your wire. So the same kind of Kirchhoff law applies immediately here, and it works in stationary conditions. When you don't have stationary conditions, strictly speaking, you're not yet there.
Yeah, thank you so much, Danila, for this very educational talk that you gave here. And